Hello friends, in this video we are going to discuss the Ekeeda diagram in the semiconductors. So Ekeeda diagram means this E stands for energy. So K is the wave number of the wave, so equals to 2 pi by lambda, and this lambda is the wavelength of the wave. Now we want to draw the energy versus the wave number diagram for the semiconductor. That means in the y-axis we want to plot the energy, that is E, and in the x-axis we are plotting the wave number k. So for that, let us go into the bond diagram or bond model of the semiconductor. So the bond model of the semiconductor looks like this, where at every cross points between these lines will have a silicon. So let us take, this is one silicon, this is another one silicon. So all these cross point will have silicons. So these are the silicon atoms, and in between there are the covalent bonds between the silicons. In this way, there are so many silicon atoms at the every cross section of the covalent bonds, and with every silicon we know that there will be 4 covalent electrons. Similarly, here there will be 4 valence electron. Similarly, here there will be 4 valence electrons, and this atom of silicon will also have 4 valence electron, and this atom will also have 4 valence electron. So in every covalent bond there are 2 valence electron in the sharing mode. All this thing comes from the bond model of the semiconductor. Now let us assume that we have doped this semiconductor or silicon by an group 5 impurity. So if I dope this with a group 5 impurity, then let us take, I have replaced this silicon atom by a phosphor atom. So this is my phosphor atom. So this phosphor atom, that is this total black circle, is the phosphor atom, and this ring circle is for silicon. So we can say that now we will have a free electron. So the free electron, so for this phosphor atom we will have this free electron. So in similar way, if we dope other silicon atoms by a phosphor atom, then suppose there is also a phosphor atom here. So this phosphor atom will also give a free electron. Let us draw that free electron as, so this will be the free electron contributed or given by this phosphor atom. Now let us apply some external potential to this material. So let us apply a positive potential here and negative potential here. So this applied electric field will attract this electron according to the direction of the electric field. That means this electric field will tends to repel this electron towards this positive terminal. So the electron will move in this direction and this electron will move in this direction. So during this movement there can be many other forces that can be produced inside the semiconductor, that so the total amount of force, we can say that it will be, so the total force applied on the electrons inside the semiconductor has two components, that is, first one will be external forces, that is due to the E applied, and second one will be internal forces due to, now let us see which are the internal forces present inside this semiconductor. So when this electron is moving with respect to this applied electric field, so there can be Coulombic interaction force between this free electron and this bound electron, or there can be Coulombic interaction force between different free electron, or there can be Coulombic interaction force between this electron and the holes in the semiconductor. So that's why the internal force that is acting on this semiconductor electrons or free electrons will be the Coulombic interaction force between the free electrons and bound electrons or holes. So we can say that the total force F total will be equals to F external plus F internal. Now according to the Newton's law, we know that force is equals to mass into acceleration. Now inside the semiconductor, the total force acting on the carriers are external forces and internal forces. So we can say that this force equals to mass into acceleration equation should be valid for this term, that is F external, and it can be also valid for F internal. So to incorporate this information that there are some internal forces inside the semiconductor along with the external forces, we will change the mass of the particle or carriers and will tell them that they have some effective mass, and this effective mass will take care about the internal forces happening inside the semiconductor. That means the effective mass value will take care the value of the internal forces inside the semiconductor. So we will write the Newton equation for this charge carrier as F total is equals to mass E into acceleration, and this ME is the effective mass for electrons, that is free electrons. Similarly, we can write that force is equals to mh into acceleration, and this mh is the effective mass for holes. So we can say that the mass of the carriers are changed due to the internal forces are present inside the semiconductor. Now we know that the inside of the semiconductor, the carriers are moving in a random fashion, and this random fashion movement is called as Brownian motion. So we can say that the carriers will have some kinetic energy. So kinetic energy of the carrier can be written as half m v square, where v is the velocity of the carriers. Similarly, we can also say that there will be some momentum of the carriers, and if we denote this momentum by small p, then it will be mass into velocity. So let us name this equation as equation number 2, and let us name this equation E as equation number 1. So we can say from this equation number 2 that the V value will be P by M. So this velocity value is nothing but the momentum by the mass. Now if we put this velocity value in the equation 1, then we will have that E equals to half m v square, and v is nothing but p by m, so p by m whole square. So ultimately we can get half m p square by m square, or we can say half p square by m. According to the de Broglie hypothesis, we know that the momentum p is equals to h cut k, where h is the Planck's constant and k is the wave number of the wave. So if we put this value of p in this equation 3, then we can find that E will be equals to half P equals to h cut k, so h cut k whole square divided by m. So it will be h cut square into k square divided by 2m. Now we can write this equation in this formation, that h cut square divided by 2m into k square. So we can write the final equation as h cut square by 2m into k square. So this equation is nothing but a parabolic equation, because this will be a parabolic equation for E and k, because we know that if x square is equals to 4ay, and we can write, we know this is a parabola equation, general equation. So from this equation we can write y equals to 1 by 4a by x square, and this equation will give a parabola in this manner. It will be the x axis, it will be the y axis. So the parabola will look like this way. So this will be the parabola for this given equation. So we have found the equation like this: E is equals to h cut square by 2m into k square. So if I compare this equation with the above equation, then we can see that if I plot the k value with the E value, then it will also be a parabolic equation, and the parabola equation looks like this. So this will be the plot for this given equation, and this graph is called the Ekeeda diagram. of the semiconductor. Now we can see that E equals to h cut square by 2m into k square is giving a plot like this. Now we can also say the plot can look like this. That means these two graph 1 and graph 2, can represent these two equations. Now graph 1 and graph 2 are having different curvature. So let us see how to find the curvature of the parabolic plot. For that we have to take the second order derivative of this equation. So curvature of the parabolic plot can be given by the second order derivative of the equation. So let us find the second order derivative of this equation. So we have the equation this. So if we find the first order derivative, so it will be dE by dk will be h cut square by m into k. Now we can write this equation like this: h cut by m into h cut k. So this h cut k is nothing but the momentum of the particle, so we can write h cut p by m. Now if I take this h cut in the left hand side, so we can write 1 by h cut into dE by dk is equals to p by m, and p equals to, you know that, mass into velocity. So it will be mass, and this mass must cancel out and will give the velocity. That means we can say that the first order derivative is giving the velocity of the carrier. Similarly, if we find the second order derivative d2e by dk square, it will give h cut square by m. So from this equation we can write 1 by h cut square d2e by dk square will be 1 by m, and this is nothing but the curvature of the parabolic plot. That means the curvature of the parabolic plot is inversely proportional to the mass of the charges or carriers. So if we have a plot like this, suppose we have two plots, two Ekeeda diagram. First diagram is this one, and second diagram is this one. Let us name this diagram. It is the graph 2 and it is graph 1. So this graph 1 is having higher curvature value. So we can say that it the carriers on this graph will have lower mass because the curvature is inversely proportional to the mass of the particle. Similarly, the graph 2 is having lower curvature value, that is the carriers on the graph 2 carriers on the graph 2 will have higher mass. So in this way, the curvature of the Ekeeda diagram will define the different mass of the charge carriers. So this is all about the Ekeeda diagram. Thank you.